welcome everybody to this session. It's my great pleasure to present to you Professor Sami Haddadin, who is the director of the Munich Institute for Robotics and Machine Intelligence in the Technical University of Munich. And he holds a chair in robotics and systems intelligence in the TU Munich. And previously, he was in the University of Hanover, and he's best known for contributions to tactile mechatronics, contact-aware robotics, and safety methods in human-robot interaction, and autonomous manipulation learning. And he has a long number of awards, which I'm not going to list in the interest of time. And without further ado, please.
Much for the kind introduction. And I have a title that is called Tactile Robots Building the Machine and Learning Itself. So I'm going to give you a little bit of an overview about some breakthroughs that have happened in robotics that especially make it interesting to look at robotics from the computational side more. So to a large extent, for many decades, robotics has always been this more mechanically, electronically driven discipline. But I think over the last 10, 15 years, we see that many of the innovations that actually came out of robotics have impacted AI, and now probably also robotics is going to kind of benefit from this to a large extent. So this is obviously work with many contributors, so I'm going to give them credit before the talk, not as usual after the talk. So this is obviously a joint work with many people I've been having the pleasure to work with, and also people who are not in the let's say public or academic sector. So companies I've been also founding together with other people, and they have been contributing a lot to the things I'm going to show today. And I think I would like to start with a little bit of an anecdote, because I think it kind of explains quite nicely where AI and robotics are kind of recently and what happened. And we all know that in the AI field, there have been kind of tremendous impacts. There have been very famous experiments. And many of you obviously know that Google's DeepMind system was beating Lee Sedol in 2000, I think it was 16, in the game of Go. So one could see that the computational efforts that were done were tremendous. That's one part, but also the result was outstanding. So in fact, the AI was beating Lee Sedol quite significantly. However, if you look at the system, and if you look at it from a not pure software-driven perspective, but from a robotics perspective, you ultimately need to ask yourself one question. Who the hell is the person on the left side? If on the right side there is sitting Lee Sedol, and in the background the AI is telling the moves, then this, and we all agree this is not a robot yet, so this has to be a human. So the physical action of executing the AI commands in the real physical world still needed to be done by a human. And interestingly, when this came out and I saw it as a roboticist, I thought, oh wait, this is actually something that I've seen many years ago when I was still in high school. So in high school, this was the big revolution. This was the other big AI revolution 20 years before, where IBM's Deep Blue beat Garry Kasparov, the world-famous chess player, nowadays more politician. And interestingly, the same question you could ask, except for the person sitting on the other side of the table. So on the right side, there is a person. He's one of the main developers of the system, but also the same question. Who is that? Well, it's the human that actually takes the orders from the AI, executes the steps in the real world, and then is able to play chess basically with Garry Kasparov. So the physical embodiment, the physical implementation of the moves of the AI system seem to be still a kind of a challenge. It sounds a bit unreal, right? As a human, we would say, well, that's super easy, right? We can all do it. But interestingly, the actions that seem to be easy for humans seem to be very hard for AI and vice versa, right? So computational problems seem to be very hard for us. We need to be trained. We need, it's kind of thought to be the essence of intelligence, but if it comes to physical actions, AI is far, I mean, like light years behind humans. Kind of interesting if you think about it. And for us, this is some very subconscious part of our intelligence, and we don't consider this to be a very unique thing because we all can do it. So interestingly, if you care about these questions, then you come into the field of robotics. If you think, well, physically manifested embodied intelligence that really tries to interact in the physical world more than pure communication, but actually action, right? Then really robotics comes into place. And robot systems are a bit distinct from at least the modern AI systems that are rather data-driven and procedural in nature. So AI systems in the physical world, they need to interact with the physical world. So an interaction, as we all know, is not a choice of directionality. If I touch something, it touches me as well. So action and reaction applies. The physical laws are applying. We cannot choose that. That's kind of inherently in the physics. They are dictated by physics. So therefore, we have an intelligent sensory motor body, you could call that, right? Similar to humans, we've got a sensory system, we've got a central nervous system, we've got an action system, so the muscles, and we've got the topological, let's say, high-level characteristics that we all have as humans. And then obviously the algorithm that would be the central nervous system and then obviously the brain and the human would need to be interactive as well. It cannot just be dictating commands and hoping for the body to be able to embody or implement these actions. It has to be also interactive and learning enabled by itself. And obviously the central question that in the AI community is often the question is who sets the goals. Obviously the goal is being driven as achieving a certain state in the physical world. That obviously is a high-level cognitive action that has to be taken place. That itself is also a planning and perception action loop. All right, so these classical examples show that physically embodied intelligence, let it be biological, let it be artificial, is a little bit different. So it needs a little bit different approaches, also from the algorithmic standpoint. So it's systemic approaches that are in nature, understanding that interaction is at the core of what these systems do. So you cannot, for example, apply a force to the environment because the environment applies the force back to you, just as a very naive and simple example. It's not a choice. So it's not like you can speak and you can at least to some extent decouple the source and the sink. So it's a systemic process, and this has to be reflected in robotics. And then obviously the skills that we want to give the systems are not just in one domain, they are kind of reflected in various dimensions, and they typically go into kind of the domains of being represented by the functionality, the goal, and the algorithm. And obviously we need to take care about the energy problem and the memory problem. So we cannot have infinite resources. Let them be even quite substantial, but they still need to reflect the constraints of physics. Meaning, if you want to have a mobile robot, if you want to move in the real world, if you want to have an autonomous car, we all know that the energy problem is one of the most important ones. And it's not just the energy supply, but also the energy consumptions of algorithms, as all of you obviously are aware of. And then the actual skills that we typically care in robotics about is locomotion, manipulation, and interaction. And obviously, manipulation and locomotion are also interaction problems in nature, but then obviously the interaction with a human needs very distinct approaches. It's not the same as walking, so we interact with the ground or with the environment, or manipulation, where we typically interact with objects, with passive objects that have physical properties, but in humans we interact with other agents or robot-to-robot communication. It's another form of interaction. All right, so and then we have one big challenge in robotics all over the world. We are kind of doomed to be told that robots steal workforce, right? They steal jobs. That has been a prejudice for many, many years. And even if you talk about AI, I mean, we all know that all the covers are typically robots that then take the jobs. It's never a binary code or something. It's always this physical manifestation. And this is in Germany a very famous newspaper. It's like our Newsweek, you could say, and Der Spiegel. And in 64, 78, and 2016, they were kind of always making this narrative that robots will steal the jobs. Implicitly, on the left side, it reads automation. So the rise of automation after the war in Germany was obviously very, very important. And then the computer revolution in 78, you think about it, I mean, it's kind of, retrospectively, you're not really sure how to respond to this kind of statements. And 2016 is computers are taking away the jobs. But interestingly, and this was just, I think, 4 weeks ago, there's another important newspaper in Germany. I know there's many of these in the world. I just showed them because Germany is very conservative, as you know. We need to think first, then we move, then we think more, then we move a bit more, and so on and so forth. So we think everything through right from the beginning, and only then, if we're 100% sure it makes sense, we start moving. So, and this is kind of interesting, is the Handelsblatt. It's a kind of more economically oriented paper, and it shows this very famous, picture from New York when they were building the skyscrapers. So the famous workers sitting, at the high rises. And typically, if you talk about robots, we're always robots, robots taking away the jobs. But now it says the robot as rescuer. Why? Because we have labor shortage, because we have high risk jobs, we have the demographic change. So these are all massive, and I mean it, massive challenges that our societies are facing all over the globe. And more I think society is at least starting to understand that automation, that robotics, that intelligent smart machines that use AI algorithms for this matter are part of the answer. So, and what would be the ideal process if you want to design these kind of systems? So obviously lots of it is typically system design, but more and more we see is if you look at cars, if you look at autonomous cars, drones, and so on, the software part becomes much more important. Right. So I think what is interesting, if you look at the overall design cycle of these machines, then ideally what you would like to have is that you decide on the objectives of the system. So is the system supposed to, bring you from A to B, or it's supposed to grasp a million objects? It's supposed to open doors. So what's the goals? What's the objectives of the system that you want to design? So how do we design these systems in a hardware software co-design process ideally? So first you come up with a design that typically starts with topology, right? Humans have a certain topology, animals have certain other topologies. Every real physical manifestation has a topology. Then you want to produce these systems, right? So meaning you want to create them. In biology, we call this recreation, right? Or reproduction, sorry. So reproduction. In real systems, we need to manufacture them. Then think about it. If you want to power them on, the systems still don't know anything about themselves. Now comes the big problem in embodied AI, that these systems need to be aware of themselves. They need to understand, who am I? How big am I? What's my articulation? How do I interact with the world? So similar to if you look at little kids, that's exactly what they do when they basically grow up over the first year or two. So the self-awareness have to be created that ends up in something we call the body schema. Okay, this body schema is kind of the own representation of your own existence that gives you the notion of how to interact with the world and how to interact with other entities. And then you want to be able to control these motions. You want to control interaction. That's very important. Motion is not interaction. Actually, all of you are right now interacting with the world. And your internal body control is active all the time, just making sure that you sit the way you sit. And that's a pretty complex process. And this is not motion. It's internal motion in your muscles that has been learned and controlled over years and decades to be able to be that delicate as you feel. So none of you fell over the last 10 minutes. That's an amazing thing, I think, that was given by evolution to us. So, and then this interaction process, that active interaction with the environment, with the objects, with the humans, is something that these embodied agents need to learn. And then ideally, you have a set of skills, right? As I told you, manipulation skills, the locomotion skills. And today I'm going to talk a lot about manipulation. So how to grasp the world and how to interact with the world and how to make this in a purposeful manner. Because this seems to be also in humans the core skill that made us intelligent. The co-evolution of the hand and the brain is known to be really bound to each other. Okay, so, but this is a long way to go there. Can we actually, and this is the loop I close over the end of the talk, can we do this automatically? Because we actually have tremendous barriers in robotics, especially if we think on the I think algorithms and sensors side. We have done tremendous process, but we are hindered by the fact that still many of the design and synthesis aspects in robotics are manual, and this is kind of limiting the progress in the entire field. All right, so, but what does this mean? What is robotics all about? So many of the things I just showed you, I want to give you a little bit of examples, how we take inspiration from the human in particular, because, I mean, there's no reason to say we need to copy the human. No, we take inspiration from the human because, well, it's one of, as in chess or Go, we have similar goals, but unfortunately they are a bit more complex. So the topology, the actuation mechanisms, the sensory motor system from the human is something that has inspired roboticist, you could say, since Leonardo da Vinci. He has been understanding the topology of the human, the anatomy, and the mechanism in his famous automata. Maybe some of you have seen them. And this is essentially what has been guiding robotics to a large extent, because form follows function, right? So this is something that, especially in physically embodied systems, is 100% true. A car is, how to control a car, how to steer a car, absolutely follows its functionality. Right? So it's not that it is a choice. There's a steering wheel, therefore you have to control the steering wheel. There's wheels, therefore you have to control the wheels. Same thing for a plane, for whatever that physically manifests. That's the big difference to pure computing. Okay, then obviously one important aspect is the intelligence in the body. Sometimes we call this embodied intelligence, the emergence of what we know to be the homunculus, so the representation of the human brain regarding, how much volume of my brain, of the cortex, is responsible for parts of the human functionalities. Obviously, the sense of touch, the manipulation, is by far the biggest ones. And this is exactly what we have been bringing into robotics. So robots with an artificial nervous system, with an artificial sense of touch, and making sense out of interaction. So it seems that in the human intelligence, the interaction with the world is one of the core things to understand before we can actually generate true intelligence, because it's something that has to be exploring the world, to interact with the world and make sense out of this world. So this kind of highly relates to the picture I gave you on the on the systemic interactions between the sensory motor body, the AI algorithm behind, which is basically central nervous system, you could call an artificial central nervous system, and then the interaction with the world. So, and then obviously the body schema. I was talking about this earlier. That's something we all know from little kids, especially when infants, they start to do these motor bubbling skills, right? So this comes basically for free. And this leads to a kind of an optimization process in our own body. And we have been reproducing these kind of things in AI fashion, you could say, that our robots are basically able to be switched on. They move around a little bit. They explore their own topology, generate that automatically, and it doesn't have to be done manually anymore. So these kind of approaches give artificial embodied systems the ability to automatically generate intelligence on a, let's say, body level. And that would be the basis, because these things are really important. If you don't know what you are, where you are, how you interact with the world, it's very hard to do this purposefully. I would even argue it's impossible. Then you start to get these locomotion skills. That's interestingly, one of my students has parents that filmed all of his steps when he started. So they have all these kind of motions. So we could study a little bit how he was doing. Seems to be normal. He's walking quite fine. And from this, obviously, the principles of locomotion. So this is the only thing I'm going to talk about locomotion today. But just that you know that this is obviously a very important aspect in robotics. So locomotion is a highly dynamic process. Many of you know Boston dynamics, obviously, right? So many of these things are in some form still pure control. So they are understanding fundamentals of the body, but they're still missing the intelligence in the autonomy, the learning, and so on and so forth. But still, it's very hard to do these things without understanding physical principles. So that's kind of an important aspect, that you fuse physical principles and learning principles together to really build physically embodied AI systems. And then obviously one of the key skills in humans, that's kind of now where we are today. That's my daughter when she was 4, trying to open a door, and I gave her 10 trials and she did it in 7. So that's kind of the key skills we have. So we're not yet at the super complex thing. So it took about 1 minute. And nowadays our robots in the lab can actually do the same thing with much less, let's say, learning abilities. Let's say they're about a week old, okay? And then just within a few minutes, they're able to automatically learn how to open doors, how to insert keys, various keys you're going to see later. So these skills are true skills that even do transfer learning. They do incremental learning. So they can now build on skills. That's kind of the essence where we are as of today. So that's not anymore, in the future. It has not been like that for many years. But now robots are able to autonomously acquire these kind of motor skills, right? Which is very hard. And if you think about the examples I gave you with the Go and the chess, so finally we can automatically grab yesterday we had a great interaction with the students. So we cannot only grab the skills, but we do these insertion processes, do these manipulation, fine manipulation skills. So a little bit the things in order to operate the world in which we live in. Okay, and then obviously the fusion of various sensor modalities. So we need to be able to not only have interoception, so the motion of, where am I, how do I interact, but the fusion with the visual skills, with auditory skills, and so on and so forth. So obviously multimodality in reality is absolutely important. It's very interesting if you look at humans, how bad they perform if you reduce one of their senses for some time. They need to compensate, they need to learn. It's a fully new learning cycle that you implement there. So these kind of things are really important. How do you fuse visual and proprioceptive information, tactile perception, so visotactile loops, such that you can really have human level performance, in particular in the interacting with unknown environments that you have not been seeing before. This generalization is extremely important because we simply cannot generate all the data that has never been there. So the humans need to learn in the loop. So therefore reinforcement learning obviously is one of the preferred choices when you look at these systems. But this is just very recent advancement. So let's look what happened 2015. Let's take a step back. That's kind of exactly what happened 2015. I did an experiment with my daughter. She was making a big mess in our living room, and I told her, I was wondering about learning algorithm, and I told her, so if you take this key and you can open the door in less than 10 trials, you don't have to clean up. So I set the reward, right? So it's kind of an interesting way to do experiments. I've got 3 kids, so I do all kinds of experiments with them. And what was happening was that after 10 trials, she was successful. It was 7, in fact. So I was wondering, maybe it's 1, maybe it's she will not be able to do it. This was the time where big data, machine learning was really deep learning was taking off, and in the robotics field that was not happening. That was what happened in the robotics field. Somehow it's kind of devastating, right? So we were not there even close. So the best groups in the world were competing 2015 in the Double Robotics Challenge, and I mean, let's face it, we were not even close to where my 4-year-old kid was back then. So let alone from the Garry Kasparov of key opening. Okay, so that's a very different challenge we had there. All right, and then if you look at it, why is it so hard? Why was, for example, the advancements in mobility so much faster? So autonomous driving seems to be there to some extent. Well, in fact, if you look at biological systems, mobility has been there very early. Also, I mean, every single cell organism is able to do navigation, to do mobility. Very simple, right? It seems to be evolutionary, one of the earliest concepts. But if you look at manipulation, primates are the ones that really could do it. So this took billions of years of evolution, co-evolution of brain and body. So there seems to be something fundamentally more complex in manipulation and interaction in the physical world than purely navigating around it. So I think this is just an example that tries to understand that. And interestingly, this has always been a question in robotics. So even if you go back to the early days of robotics, I mean, it started with very, very, big positioning machines. That's the first industrial robot by Joe Engelberg and George Devil. That has been actually the first robot that industrially was able to be combined with a computer. So it was actually the Puma 560, which is still the grandfather of every first generation industrial robot. The first computer controlled robot. So a 6 degrees of freedom, so 6-axis motion that could be controlled by a computer program, right? So this is kind of how things started. But at the same time, essentially, the early days of tactility already took place. So no one ever wanted to have a motion robot. Everybody always wanted to have, I mean, Shaky was a mobile robot, but anyone else who did the manipulation was questioning, or was asking the question, can we interact with the world? Can we grasp the world? How do we introduce tactility? The sense of touch is the most important sense in physical reality to produce intelligence, okay? So this was not new. In the early 80s, many famous people like Osama Khatib or Gerd Hilsinger, Bruno Siciliano, and others were doing the very, very early basics. How can we make robots force sensitive? How can we make them reactive? So for example, reactive planning based on computer vision. So this was always very early on already in robotics, but it never hit the reality. It was never punching through to translate into real industrial or real healthcare robots or anything like that. It was always in this laboratory environments. So the industrial robotics generation has been the first one. As I said, the Puma 560 was the father of all the standard industrial robots. And you can have here hundreds and thousands of different systems. And then only maybe 15 years ago, 18 years ago, in fact, the first so-called cobots came into the world. So robots that could be operated with humans without safety fences. They had a kind of an emergency system, or still have, that if you touch them, then they stop. But it's really a very crude system still. And then only recently, for the first time, we have systems, and we were kind of, I think, at the core of this development and also translation to reality. So these systems are now industrially available. They are considered the 3rd generation of robots. Also made it to cover of New York Times, National Geographic, and so on, which I think was kind of nice to appreciate this big breakthroughs, are the first robots with a true tactile sense of touch in reality. So not only in my lab. Okay, and to be honest, it took 15, 18 years of basic research and many people before to do some of the basics. And now we are there that these kind of things can actually be realized. So, and obviously there have been many key influences, and many of them really go back to probably many of the names like Raybert or Khatib or Paul, Hilsinger, Atkinson, Hollerbach. So many of the people also in AI were doing tremendous impact, were originally trying to solve these problems, right? In the 80s, in the early 80s, actually some of the concepts were proposed 78 or 79. So this has been always a dream of robotics to have robots in the real world, but we were just technologically not there. So, and then there has been lots of work on what we call collision handling. So how do you interact with robots? How do you give them reflexes? How do you do robots with flexible elements? We are all flexible, right? There's so much intelligence in the human body just due to our flexibility and compliance. So how do we make use of that? And then obviously all the great works that came into manipulation learning from Eisbert, from Peters, Shah, and others who have been really kind of seminal in the way that they introduced various concepts into robotics. So these kind of systems became now reality. And just to give you one example, I mean, obviously just very, very anecdotic, but what's the difference? So that's a standard positioning robot, right? Obviously very dangerous. None of you want to be around it. If you look at the collision system of a collaborative robot, then it doesn't really have a sense of touch. It's more like a car that runs into something and doesn't kill it, right? So it's still very, very, I mean, brutal in some sense, you could say. And then comes this final generation, really with proprioception and the sense of touch and a reflex system similar to humans. By the way, the reflexes that you need in order to touch the hot plate and retract are about 60 milliseconds. Just the reflex. These systems are now at a millisecond, so 60 times faster than a human. So that's true superhuman skills that finally could be reached. And how is this possible? So how do we get to this tactile performance, and then how do we exploit it in algorithms? Because this will open up all the things like in deep learning, the difference between GPUs and CPUs, and the ideas of essentially new algorithms that enable that. So the tactile performance comes from mimicking what we have in the muscle systems. We have the Golgi tendon organ, which is essentially a force sensing device. So we are able to measure our internal forces. That's built in all of you. Okay, so this is basically what we copy, obviously with technology, and then put a lot of control and learning algorithms on top. And with this single sensor, like when you have a computer vision sensor, point clouds enabled everything in perception, right? So these two kind of analogies are drawn. So GPUs and point cloud sensors. So we have now sensing and the right hardware. So dynamics models, interaction control, reflexes, machine learning for manipulation, and tactile programming became possible. So, and what do you get? So you have robots that weigh 17 kilograms, and with intelligent algorithms that are aware of their own embodiment, you can take these robots by the hand like a little kid. So now you can show them stuff very easily, very, very gently. So this is the true first robots that are tactile in nature. And they are compliant. So they basically have artificial muscles all implemented in software. So these robots don't know what curvature is there. And they just give in because of their compliance. It's active compliance. It's really kind of an artificial muscle system. And you can actually change the environment online. And the robot still is able to follow without any algorithms that need to plan. So it's pure built-in intelligence, similar to what we humans do, right? We can follow curves and lines very naively, very intuitively, because we are built like that, right? It's kind of built in the system. So it's in robustness and intelligence that gives us the ability to respond to the uncertainties of reality. This is a fundamental principle that is built in any biological system that has to interact in the real world. And then safety reflexes. So a robot that cannot fulfill Asimov's famous law of not hurting humans, so that's how you do it, right? That's a nail. The robot is blind. It's pure tactile, and it contacts the balloon and responds so quick that it is not obviously destroying the balloon. Okay, that's, I think, the safety system that you want. Why don't we have autonomous cars yet everywhere on the street? Because safety is still the main problem. But if you want to go to reality, you have to make sure that humans are not hurt. Right? So this should be our main priority in AI systems general. Do not hurt, do not harm, a little bit like the oath that medical doctors take. So, and obviously what is really important is intelligence on the, the levels that you don't see. They're so fast in milliseconds that you want to detect collisions, contacts with environment, which is the manipulation problem, from the early phases to detect, to classify, so detect the contact, where is it, what kind of signature does it have, what's the purpose of the contact, is it a collision, is it a potentially harmful contact, am I manipulating the environment, am I handshaking, and then reacting to it. So this is kind of a very fundamental aspect. And if you want to be able to do that, you need to be able to fundamentally detect contacts in arbitrary environments. This is just an experiment showing you that this step change in robotics has taken place because these systems, the collaborative level, are essentially not able to detect the contact with, I don't know, this maybe 10 kilograms. I think none of you have this kind of low sensitivity. So all of you can detect very light contacts, right? So like the balloon, but not as fast as the robots, but in principle, yes. So, and this is exactly what you need to do. You need to have systems, it's like a visibility map, it's like the retina and the, receptibility on the tactile sense. So depending on the velocity and the contact dynamics, can you not see, that's the black, or can you see the collision? So that's a fundamentally new generation of robotic systems. So after, I would say, 50 years of basic research, finally these systems are realized. Okay. All right. And what can we do with that? There's so much we can do with it. Obviously, we can now respond to an environment. We can respond to humans. So we can actually show different reaction strategies. So robots can now do all kinds of things, and they move in proximity to humans. You can basically talk to them via haptic interfacing. So depending on how you touch them, they speak a different language. Okay, so they go faster, slower. You can, show that reflex. They go back in the task. They do all this autonomous planning, just in milliseconds, because they know essentially what's the task. The task is to get that cup here. And if you see the collision during the phase where the cup was not in the gripper, the robot was compliant along all axes. Now it's obviously aware of the object it's carrying. So if you now take it away out of the task, it holds the cup. Imagine it's not spilling water, right? So the idea is that this intelligence in the system, this embodiment, has to be in the AI of the system, and it needs to understand what's the task and be able to respond to that. So these kind of low-level reflexes are actually on a way that humans cannot do. We are basically training them over a long time, but we cannot plan or let alone let them be dictated by AI algorithms or by intelligence itself. So, and then obviously we need to control the world. We need to be able to control forces. So if I tell the robot 7.8 newtons, regardless of the interaction, this is a very principled experiment. Whether it's foam, whether it's rubber, or whether it's wood, it has to be 7.8 newtons. This is something that, by the way, you guys cannot do. No human is able to exactly control that force. It's actually something that now makes these machines safer than humans can ever be, which I think is an important aspect. So it would be such that now with these robots, you can actually have tactility and interaction abilities that potentially with the right algorithms can now be safer than anything we've done in humans. So this is our GPU, you could say, in robotics, right? So now we have finally robots that have this tactility, that have these interfaces, and then you can now do robots that can do all kinds of things that can, for example, do things that for you are very simple. But if you look at the reality, no robot has ever polished a car. No one has ever done, the famous trick from Karate Kid. So, so these kind of things can now be done. And by the way, the robot has no idea it's a jigsaw. It does not know that there is this impact. So it just tries to polish. And with these disturbances in the environment, that's basically the robustness of these algorithms you get. They can actually deal with totally unknowns in the environment. So the robot does not know how long this object is. Just by feeling and low-level AI planning, basically it's able to respond to these kind of unforeseen environments in millisecond decisions. On the left side, you see how I think, I'm not sure it was shown already, the table is basically moved by a human all the time, and the robot is replanning on the spot, while it's very accurately applying a force to the environment. So this is really now where we are basically standard. What is this good for? So it's, for example, good to draw Elon Musk from the distance. That's something, the robot here has its sense of touch. The artist on that side sits and uses that robot as an avatar, right? Sees only that visual representation, and the robot is basically the prolonged arm, but obviously via a distance. So the robot is basically managing all the low-level things to, in the end, have such accurate drawings without being on site, without being physically connected. So it's really kind of this intelligence, low-level intelligence, tactility, and control that gives you that kind of authority on remote interaction, which obviously in the pandemics would have been great to have everywhere available, right? I mean, think about telemedical applications, for example. Okay, so what can you do with it? Well, you can now automate all the things that could not be automated. So you can automate electronics. Electronics is basically done manual still today. If you think about our wonderful digital devices, they are done in massive manual labor all over the world, right? This is something that is not automated. Millions of people do very, very, uncool jobs to essentially manufacture these devices. And in particular, why is this the case? Well, because you know how easy it is to break a glass of an iPhone or other smartphones. So this kind of way of automation is now finally possible. And what is kind of interesting, so I also founded a company called Franka Emika. It's Germany's robot manufacturer nowadays. And these systems have now basically evaluated anywhere in the world. Every big company, every lab in the world that does manipulation research, or most of them, are actually using that systems, including NVIDIA is in the Omniverse. You see it in Intrinsic being used. So these kind of systems are now being enabling all the machine learning communities in the world in robotics. So this is really now the hardware we needed. And I think what is really great, and it's not only in research, but also all the technology drivers in the world are now understanding. But if you look at the big, this is just one example, at ICRO, which is the biggest robotics conference in the world, out of, I think maybe we have 120, 130 manipulation research papers, 100 of them now use that robot. So it became the de facto standard in the world to basically do your manipulation and manipulation learning research. So, and same thing, just as a final conclusion to that part of the talk. So this is now where we are in terms of systems, and then I'm going to talk how we use that in all kinds of new types of learning applications. And what I show you now is a video. There's unfortunately no sound. Do we have sound, by the way? No, there's no sound. Oh wait, no, it's me. It's me. Sorry, I think I switched it on off earlier. Or it's...
Frank Emeka pioneered robotics with a human sense of touch and is committed to create a robotics platform to revolutionize industrial production. Now, introducing Franke Production 3, the robotic automation tool for everyone. In-house designed, industry-leading torque sensors in all 7 axes allow for a large range of motion and poses. Intuitive user interface allows anyone to start using Franke Production 3 in minutes. Just plug and use. Designed to be intuitive, smooth, effortless hand guiding for precise and easy positioning. Compliant with industrial robots safety requirements. With Franke Production 3, we are enabling industrial automation that allows production of anything, even a movie. Franke Production 3, dedicated to the new generation of industry players. Think it, make it.
Okay, so basically this has now become reality, which I think is great that this becomes available to people. And now I'm going to show you how this can be used for all kinds of machine learning research. So it's kind of our GPU in robotics, right? I said this now already several times. So it's really important to understand that hardware accelerates software. I think this is really, that's, you know, I always wanted to do lots of things in manipulation learning, but somehow there was no platform yet. So we basically needed to create it. And that's kind of now the solution. And interestingly, just as a side note, this is not only now enabling manipulators, but also if you look at, actually Theo was my first PhD student many years ago. So what Theo has been doing in his time was, okay, let's crash a drone, or can we enable drones also to do the same thing as we just saw? Okay, so drones with a sense of touch. Okay, why? Because this gives drones the ability to, you know, fly around, and if they are autonomous and they fly in the woods or whatever, they crash into stuff, they don't crash, right? They just bump into it and they can continue. And this has been commercialized as well with, maybe some of you know it, Skydio, it's a US-based company. And you can not only use it for bumping into stuff, but also landing and taking off during wind, very strong winds. So what you see here now is where the drone autonomously, that's all autonomous, by estimating based on these sense of touches, the wind at the moment, and is able to autonomously land despite this heavy wind. So, and not only for drones, but also now, newest thing, for mobile systems. So mobile systems typically have these bumpers, right? They don't have a sense of touch. But if you think about cars, autonomous cars, I told you, I mean, they to be crash into stuff, then you try to minimize the danger. But what happens if cars, autonomous robots, essentially have a sense of touch? So basically, the same thing, the sense of touch in the drivetrain, we just published this at ICRA, that is able to very sensitively detect the contact. So this is a 100-kilogram platform that has the sensitivity of, I don't know, of your hand, basically. You can obviously switch it off, right? So it's a software thing. But obviously, so it's always nice to tease the developers with this. But I think it's clear that this kind of technology is very, very crucial. If you want to go robots in the homes, robots in the healthcare sector, how do you want to do this if you cannot do, you know, safe interaction with the world? That's absolutely crucial. Okay, and then last but not least, we actually solved this problem, I think, for general robots. So this is multiple contacts, slow-mo, and the robots are able to detect and isolate and estimate all these contacts at the same time. So we can actually do this for fully fledged humanoids, even at millisecond, faster than millisecond ranges. So now you have basically extremely fast beyond human capabilities to detect and react to collisions in principle. One thing that now has to come as a next breakthrough is obviously interaction via tactile skins. That's something that is still not yet as there as you would like to have it. So there needs to be something done. Interestingly, this can not only be done for robots, but also for prosthetics. So other things we're doing at the moment is to generalize these things to hybrid systems, to symbiotic systems that basically share human interaction. So essentially, prostheses that have a sense of the embodiment, a sense of touch, and sense of awareness of the body picture. And this obviously relates very much to what we call nowadays digital twins. So just to show you one example, that's the last thing on the embodiment part. So you see that the systems we build, despite they are floating base, they don't know that they are connected to the human. They know that they are connected to the human, and they estimate based on available sensor information the kind of the state of the human in order to be a perfect substitute for the, in principle, gone capabilities. So these kind of ideas are essentially such that any kind of system now, prosthetics, flying, we do it now for underwater systems even. So can we make them aware of interaction, aware of their, embodiment and interaction with the world? So this kind of basic body awareness is fundamental to any really intelligent system. All right, now let's come to the actual learning. So with these kind of embodiments, can we replicate what my daughter was doing back then in 7th trial? So what you see now is basically the 7th trial when she was successful. Very interesting way of grasping things, but this obviously gets improved. So we've been doing for many years now with colleagues also from Imperial College. Etienne Burdi was kind of trying to fuse human-inspired motor control and machine learning approaches in very efficient, very small packages with robots that can do these, very hard manipulation tasks, not in days and huge computing resources, but just on a standard PC and just in a matter of minutes. So the idea is essentially to bridge the data lag problem by smart, let's say, reinforcement-based learning approaches that build on a control stack that is highly human-inspired. With this, just in a matter of 6 minutes, you can learn something that kids need 4 years and the 7 trials I was talking about before. So this is kind of the speed up we have gained. And interestingly, if you compare that to standard deep RL methods, which are end-to-end, I will show you the results. And in contrast to, let's say, human-inspired architecture with then building on top of that a learning loop, you can actually see for yourself what's the result. So on the left side, that's something we published maybe 2 years ago, our algorithm, and on the right side, if you just do end-to-end, by the way, it's really well-informed end-to-end learning. It's really essentially impossible to solve these highly complex manipulation problems just without any physical or prior knowledge in the sense of intelligence, because it just becomes intractable. Right? So we did our best for weeks to try to find a solution, but the standard end-to-end was not able. But with kind of these model-informed machine learning approaches, you could really bridge that gap. You could do the breakthrough to finally have robots that in reasonable amounts of time and super small packages of compute can solve the manipulation insertion problems. So just to give you an example, that's the cost function. They look very similar, but interestingly, any kind of standard algorithm we tried, they all ended up in basically not solving the task. So the cost remains 15. The global minimum is 0.5. As you can see here, any standard deep learning architecture was not able to do that. So I repeat it, not. So you need models. So this is now finally the things where you can really see that only deep learning and only control both cannot solve it. The standard nonlinear control is not able to solve it either. So you need to fuse. And interestingly, if you do that, then you can do that on a level that if you compare it to a human. So what we did now is, I think it's going to be published this IROS. So we compared this to a human expert that programs the same thing. He's using the robot, programming the robot, and on the left side, the AI. Obviously, the human expert is much faster in programming the system. Learning took a little bit more time. But what is interesting here is, obviously, it's an expert, that's one thing. But what is interesting is the outcome. The execution speed of the learned skills that you just saw, pushing buttons, inserting, and so on and so forth, they're exactly the same in execution speed. So the performance of the expert programmer of a robot is equal to the output of the robot learning algorithm. So which is, I think, kind of remarkable. So obviously, there's, again, still gaps with human hardware. So the human is faster if he does it himself, which is out of question. So we're not yet at human. I said this in the intro statement. But the learning that we can do now produce the same result as an expert programmer, which I think is a quite remarkable result. If you compare this to the early days of what Google was doing with graspability or OpenAI with the data machines and pushability, I think it's clear that they used huge computing resources, right? Enormous computing resources. It took weeks and months to train these systems. And I think this is now fundamentally obsolete in the end. So we can do it at orders of magnitude reduce time, cost, and much higher performance of the systems. I would even say it's only possible now. So obviously the other thing is you all have to, learned about the problem with I think we talked yesterday about it, right? About the energy problem. Yes, it's a big problem of AI. It's not a small problem, it's a big problem. So, and we all know that, you know, this very famous paper in 2019. And interestingly, if you compare it to the learning algorithms we have been doing, right? This is kind of roughly what you can assume, right? Every training cycle is about 300 watts if you take a robot, then 10 to 12 kilowatts for a server stack, and then you have 50,000 to 80,000 servers, right? So, and if you compare that to what we have been doing, it's basically in the watt range. It's one computer, one robot with 80 watts, so we're 200 watts in total for 6 minutes, okay? That's the difference. So it's orders of magnitude, smaller energy consumption than to standard deep learning-based AI. Okay, so and the interesting thing is it cannot only learn one task, it can learn many tasks. So generalization, incremental learning is possible. So we can now insert a puzzle piece or a key. So these are the three things we want to show. It's a very different tasks, right? They're not similar at all. And peg into the whole. Geometrically, they're different. Contact mechanics is different. Compliance is different. Accuracy is different. And now the first trial of learning the puzzle, you can see here, that's a very, very tight puzzle. It's actually very hard also for humans to do it. And the interesting thing is, I just do it a bit faster. So now the learning is taking place. And interestingly, we can see that the same learning algorithm with the same parameters is learning all of these tasks at the same time. So interestingly, if you use something from the other ones, it's starting to get faster. So there seems to be a transfer between tasks possible. We didn't expect that. So that's more an observation. Okay, so the learning algorithm seems to be now transferring knowledge from one task to the other one that is totally unrelated, you could say, except for it is an insertion task. But insertion is a pretty big word for basically everything we do in putting stuff into another thing. Okay, so that's a pretty big step we did there, and it took, as I told you already, 6 minutes 30 for each one of them, and the result now human level performance. So what you see is on the upper left a blind robot just with tactile intelligence, and then that's a mechanical engineer, electrical engineer, and computer scientist. I have to admit, interestingly, the mechanical engineer is the fastest. Kind of an interesting observation in that experiment. But what is more interesting, I think, is that the robot is actually in the end, and you can see how it's jamming. It's really hard. I did it many times, and I was never as fast as these three. So, and interestingly, the robot is in the end the fastest. Okay, so we are now at human level performance regarding these examples. The next question that I was teasing already is, if we learn one thing, can we transfer it to another skill? Can the robot leverage knowledge it has been acquiring before and generalize so it can even learn faster? Not 6 minutes or half an hour, but maybe it's possible in 1 minute, maybe even faster. Yeah, and the result, so we kind of classified, this is something we were currently under submission. We kind of classified tasks into distances, right? So classes of similarity, you could say. So we call these transfers interclass, interskill class, interskill subclass, interskill instance transfer, and so on and so forth. So depending on how close these problems are to each other. So different keys, they are basically an interskill instance, okay? Or a skill instance if you do the same key at different locations, and so on and so forth. So we need to kind of understand how far are skills from each other, okay? It's a very rough taxonomy that just tries to a priori understand what's going on there. Okay, and what we see here is just in a nutshell, we can see that depending on the distance of transfer that I just explained to you, you can actually see that the reusing of knowledge, so the speed up, for example, for level 1 transfer is 40%. For level 0 transfer, it's 80%. So yes, you can reuse knowledge entirely. Okay, so which means this effect is objectively there. So there seems to be now with this architecture possibility to transfer knowledge from one skill to the other at considerable speedups. Okay. And by the way, I think the best ones were 20 times in some cases. So sometimes, and this is just an observation we almost achieved single shot learning. So just taking, and it's an experimental observation. Okay. So, and now the next question we ask, okay, if this is possible, can we, let's have a robot that is supposed to insert a key for the first time. What happens if we now try to fuse many other robots that do all different keys in other places? This is the other robots you see here. And they have all different keys than the one in the front. And can we leverage the knowledge that they generate? And how fast can we learn if we do that? So it's parallelization and collectivity. So it's not isolated parallelization, it's really as a collective, essentially. Okay. So and what you see now is that if we activate, so these robots, by the way, have all cameras, as you see, just because we wanted to change the pose. So everything is changed. It's not never the same experiment. All of them are different. So it's not depending on the pose. Everything is kind of changing, and they all have different keys. So this is kind of a lock, and you have door keys, you have indoor keys, and so on and so forth. They're all different. And interestingly, if you look at the digital twin inside, so that's kind of the representation of the AI that collects the knowledge. They are, by the way, all distributed. So it's not that there is one central AI. They all have these small PCs, and they just send around their learned parameters in a kind of a distributed manner. So that's actually fully scalable. But what happens here is you see that the green ones are the successful ones, the red ones are the missed trials, and actually the red ones at some point saturate. So they don't go further. And at some point, basically, maximum robustness and maximum success could be done. And this is now what happens in reality. That's actually real time what you see. So the robots are, the first one is always negative to be, then they start immediately to essentially be able to do what they're supposed to do. So very early on in the second or latest third trials, the first robot is obviously there's some stochasticity in that process. Sometimes it's up to 5, but this is very seldom. Very quickly they start to run through the whole network, a kind of an avalanche effect. So they all are able to do their insertion tests. And then in the end, we just took, what was this, 20 seconds, right? And now we put it to the front and you see everything is different. And again, the key goes directly into the pool. That's basically out of never having, none of that robots has ever had one of these, the key in the front in their hand. Okay, so here you can see the acceleration effect, just for one example. We are still in the phase of evaluation. So if you compare this to a parallelism, and then basically this one is a little bit of an outlier here. So we still need to do the statistical analysis, but typically it's almost a single shot learning in medium, maybe 1.5 hours. Okay, so and this is not parallel, right? It's collective. It's really exchange of knowledge all over the systems. All right, so this is kind of a theory behind. I will not go into details, but basically, to sum it up, with standard deep learning is not possible so far. I've not seen it. So end-to-end, right? So it's not that deep learning is the problem, it's the end-to-end that is the problem. So you need to carefully understand where is the end-to-end taking place. It's not at the torque level, right? It's at a different level. So if you do that and you learn it from scratch, basically means you always, you need as much time as you need. If you can learn from experience, so incremental learning, you have the first qualitative increase in speed. And then if you go to collective, you've got a second learning curve. And this is it's 2 exponentials that you see. Okay. All right. So we have come far, I think. Right. I think it's pretty nice what you can do, but still there's something fundamental missing, I would argue. So we have significant problems in acceleration. So we need to basically, what I'm trying to say is hardware matters, and we cannot always wait 30 years for new hardware. I mean, this is ridiculous. So we need to work on the synthesis cycles of hardware to get the same accelerations with the next generation hardware. So this synthesis cycle that is a co-evolution of system and hardware, I think it has been instrumental in deep learning, and robotics is for the first time also there. So we need to work on that. I think it's clear that we cannot decouple these problems. All right, so I come back to my cycle I gave you in the beginning, and since I don't have so much time, I still want to go through some of the key results we have here. I want to show you some of these things can be automated already to some extent. Okay, most of them are still today manual, but it starts possible that we can automate them. All right, let's go to the manufacturer. That's actually something that is reality. So since John von Neumann and his universal constructor and the automator he was proposing, the idea of automatic assembly of artificial systems has been there. It's been one of the main concepts of AI, you could argue, and artificial life, but never been really realized. And except for some nice simulations that do the game of life, but very few of them really had realism. And interestingly, these ideas have been also in I think it's 80, right? Yeah, that's when I was born, actually. In 80 already, NASA people were kind of hypothesizing about building robots, obviously for space application. So you go to Mars, you just want to bring in stuff in, goods there, and then the robots build the robots. That would be the ideal, because then you don't have to do everything on Earth, right? Obviously, building infrastructure in remote locations would be a fantastic thing to do. So robot replications could be robot construction replication. And then the inventor of the first computer, Konrad Zuse, by the way, is a German, tried to do the same thing in the 70s, and actually late 60s and early 70s, but he abandoned the idea. He was unable to do it. And I think it's very clear why, because there were no automata, no machines that had a sense of touch. Why? Because if you want to do assembly, that's exactly what this is all about. If you want to do assembly, you need a sense of touch. No sense of touch, no assembly. Okay, so you need it. It's an absolute key ingredient. All right, and this is also why the robots we've been developing. This is just some examples that we showed at a fair. They're actually assembling themselves. So these robots are the first robots that really manufacture themselves. So it's actually a big factory in Germany where these robots, so they're not done manually by hundreds and thousands of people, but these robots actually are able to produce themselves. And this is why we can actually produce them in Germany, right? And why they don't have to be produced somewhere else. So, and this is kind of some impressions from the real factory. Unfortunately, I cannot show too much of it, but I think it's clear if this is a product, this is actually how it works, right? So you see hundreds of robots, but interestingly, with many humans in between. So it's humans and robots manufacturing robots. So this is kind of what is possible here. Here's some impressions. So this is the tight interaction that you see because of the sensitivity and the learning. You can really have robots that are basically following Isaac Asimov's famous first law, according to standards. But in particular, you have robots that can do all the delicate assembly processes, learn from the algorithm I just showed you, to be able to do that in pretty fast time. All right, so that's kind of what's there. Obviously, there's still lots of improvement until we can automatically produce something from a pure design system. But I think we have done it once, so it exists now. It's in principle possible. Okay, let's go to the design. What can we automate there? There, what we're doing at the moment is, can we automatically deduce from human understanding of the hand, can we automatically deduce design processes of mechanisms in the robot hands and synthesize the design, at least on the mechanism level, such that they are able to do what humans are able to do. Okay, it's a closed loop system. So we basically use already established, there's hundreds and thousands of these, principal ideas how to do mechanics, right? It's very hard to enumerate them, but can we actually use them to learn basically from what humans have been doing and do the recombination that has actually solved real-world manipulation tasks, such as, grasping objects, and can automatically be deduced from the human understanding of manipulation, a robot hand. So this is a fully synthesized robot hand kinematics and actuation mechanism that is able to grasp all these different objects. So from object to kinematic design. Okay, that's now with an end-to-end approach. So we basically use, similar to the learning I showed you before, we use human engineering knowledge, put it into the networks, and let the network do the rest. Okay, so that seems to be something that goes quite far. So you can actually replicate very delicate manipulation of the human with a robotic hand, at least in simulation. And this has been done for various tasks and for various kinematics. I think this is also to be publicized soon. All right, then let's go to the interaction. How can we actually learn interaction? So this is one of the last parts. So now that I showed you in reality, we can do interaction. We can now use this information to backdrop into simulations. It's very hard to do from simulation to reality. It's like this typical problem. It's very hard to generalize a special case, but it's much easier to simplify a general solution. General solution is not the simulation, it's the reality. So if you know something in reality, then you can simulate it and then you can simplify. Okay, that's the way that in robotics turned out to be the right way. So what are we doing? We're basically using the same algorithm we saw before, but now for hands, so to go more dexterous, to actually inform the next generation of hand development. What kind of things can we do? So it's the key into the whole, okay, out of the whole example that we saw before. And this is something that now can be used to pre-train the algorithms. And the next question is, can we actually generalize that such that in reality, a robot could basically learn only in simulation and then do direct manipulation of the world? So what we see here now is a robot that is learning in simulation, Muchoco simulators basically, to open door handles. And this takes a few minutes, as you saw before, to do the training of the policies and so on. And then interestingly, if you transfer that, that's the real Sim to real transfer in an instant. So that's the robot that we use for experimental validation. That was just recently. The robot is actually automatically tuning its entire compliance such that this very big difference you see, that was at least 10 centimeters. 10 centimeters of difference. It had no idea where exactly it is. And just by the right compliance, like you do in a hand, right? You do a door handle opening, you're also able to do that. Just naive, intuitively from our learning with interaction. And that was basically just out of the box from the simulator. So I think this really shows the power of AI if you combine reality with simulation and the right embodiment. So to really, transform these kind of concepts into reality. All right, then let's go to the body schema. That's the last thing I want to talk about. I have to speed up, unfortunately, but that's one of the most interesting things that we came across recently. So can we basically automate the body schema generation? And typically, it's a very complex. It's a very complex problem. It's highly nonlinear, topological, dynamic, kinematic. It's a mess. I mean, to be honest, it's 90% of robotics research, I have the feeling, was treating the body schema problem, right? From modeling to understanding and to identification. So, but basically, what it is boiling down to is that the robot is basically need to learn a sensory motor graph, the topology. So, how do what's the topology of your environment, of your own body, the morphology, and then the dynamics. So, how heavy I am, how much forces do I need to actuate myself, and so on and so forth. So, what we did recently is to automatically generate basically the topology of the system by basically using information theoretic based machine learning to essentially try to understand, from the sensory signals that we get, can we get the topology of the system? Can we get the connectivity of the different robots? So you see on the left one, this is just the robot. It has no idea which part is which, right? It's just measuring the sensory data, and now automatically the robot is basically by mutual information analysis trying to isolate which part of my body is next located to the other one. So get the causal chains, the kinematic chains automatically. Obviously, if you build a robot, a mechanical engineer will tell you, why do you do it? Who cares? I gave it to you because I designed the robot. And that's not the point, obviously, right? The point is, can you generate this kind of embodied intelligence from scratch? And if you have modular robots, if you have new assemblies of robots, if you want to have this automatically for all combinations of robots in the future, then this obviously needs to be happening automatically, okay? So it seems to be quite something. We also tried it with very others. So I'll just show you in the end some other examples. I think it's coming. Yeah, here. So with humanoids, it's also working with crawlers. So this seems to be a method that really scales well to quite complex kinematic chains. All right, the last part I want to say is in dynamics. So this is the universal equation of robot dynamics, right? This is what is all kind of boils down to in robotics. It's the core equation that you need to learn. Okay, that's the body equation, you could say. Okay, famous Lagrangian dynamics. Unfortunately, very complex, nonlinear, very nasty. Yeah, but very important because otherwise kids could not learn how to hold their own head. If you are not able to understand, at least from a sensory motor perspective, how your body works, how do you want to hold your arm? It's not working. It's not coming from nowhere, so you have to be able to do it. All right, you can machine learn it, but this will take, just for 7 degrees of freedom robots, 130 years just to acquire the data. Very naive and not really great idea to do it. So we need to have a fuse of models, basically, and data acquisition. So one thing we did recently is we tried to essentially get inspired by two of the great people from robotics, Chris Atkinson and John Hollerbach. They had major papers in robotics, including how to learn dynamic or how to system identify dynamics. And they found that this highly complex nonlinear equation I showed you basically can be written down as a linear parameters problem. Wonderful. So we can learn it in principle, right? So system identification does the same thing. Build a regressor, do the pseudo inverse, voila, it works. Well, it's a bit more complex, but in principle. So what we did recently is we actually said, okay, can we actually do a network that does the same thing? So basically a new type of neural network, which we call first order principle network, that takes physical principles like Newton's and Euler's law, combines it with the right acquisition of data, and then do a network that inherently encodes physics, and therefore is able to capture nonlinear dynamics as accurately as it gets, at least from a numerical standpoint. So basically, we came up with a new representation of this type of dynamical systems that is not the Lagrangian dynamics or the regressor form, but with a network of networks that is basically kinematic. It's a kinematic network and a dynamic network that is sequentially, and this is kind of the last parts of the phases I showed you before. And to make a long story short, interestingly, what you see here, just in a short amount of time, we end up in an error that is only numerical of basically, the blob kinematics to full humanoid kinematics. So it is able to understand its kinematics and dynamics with this kind of networks. And if you compare it to standard deep learning or other kind of machine learning approaches that do not use and utilize physics, they basically don't generalize. The errors are between 50 and 100%. So these equations are so nonlinear that it is not sufficient to just look at certain bunches. And you cannot just explore the whole space. The equations are not scaling well. So you need to basically combine, and then you end up in numerical errors. So you actually find the true solution of the system. All right, and this is the experimental results. So you see basically, this is actually also one of my daughters. when she was obviously at a different age. And basically the same idea. So explore your own body, generate the right data, use these networks, and then what happens is the robots can now hold their own arms. So like this was my boy when he was 3. No, two. Actually, at 2 you have quite a good body control, and these FOP nets are able to do the same thing. If you switch to standard neural networks, collapses immediately. Okay, so the generalization ability of pure data-driven methods are just not scaling, and they're not working for this. So this is not a functional approximation problem. Functionals are more complex, and dynamics equations are not captured in pure function approximations. Okay, I will skip this one just to say one last thing in order to get to that level. So let's assume that on the long term we can do that, but we have one fundamental problem, right? So if we can automate all of that, we could hypothetically we could automatically synthesize based on what we want to do a robot system. Okay, in the long term, I'm not saying it's probably more decades, but parts of it can be automated already and are used. But one thing that we need is we need human intelligence. We need humans to inform everything we're doing here. So what I think is now also possible with the immense, transformation we see with metaverse and digital twins is that we can now finally use robotic systems as the gateway to train fully functional physical simulators in real time. So digital twins with physical environments to inform the AI systems and really accelerate and combine not only machine learning and physics, but also human experiences on the spot basically, and feedback even. This is what you see here: physical forces from the virtual environment in real time that are almost as accurate as it gets. So I think with this, I would like to basically conclude and hope it was a little bit of fun to watch and listen. And yeah, if we have a few more minutes for questions, I'm more than happy to take them. Thanks so much.
I have a couple questions. One is, most of the examples involve just tactile, but I was wondering, maybe it's computational complexity, because like humans have lots of senses, like involving more senses will improve training times, will make it more complex, or it depends on the task.
It's a great question, actually. So for decades, people have tried to do based on vision alone. It actually didn't work. It's not sufficient. So it's actually one of these, manipulation actually turns out that you need the sense of touch. It's like, it's not nice to have, it's the one that it's a necessary condition. Not sufficient, as you say. For example, for many cases, I mean, if you don't know roughly at least where the places are where you want to do it, obviously you need global perception, out of question. So I think, obviously, I mean, you're basically pointing out to exactly what we're working at the moment. So we're working on how can you fuse, like really fuse in the fusing question, the visual and the proprioceptive tactile perception into unified models that can basically make use of all that sensory streams in the loop. So I think this is the next big question. And one big question I would also have, it's interesting if you look at telepresence applications where humans are teleoperating robots. If you give them auditory feedback, it seems to improve their abilities. It's very interesting. You would say, well, but why not sense of touch? Actually, you can substitute sense of touch. Apparently, that's now a pretty bold statement, but it seems to be the case, at least from some experiments we did between Europe and US, with high latency networks, that if you give auditory feedback, it also improves the quality of the manipulation process. So I think that these three senses are the ones that, if you fuse them really very nicely, then you can probably have step changes in the performance. Maybe not so much in the final performance, because this, in the end, is always a tactile thing. It's a local motor skill. You can do all these things, you just turn away and you can still do it, basically. But the learning process, I think, will be sped up, especially for more complex tasks, especially for tasks where you have, where if you need to find, for example, where to do the manipulation process, the global information is another necessary condition, becomes necessary. It's not necessary if you're local. So I think this is very obvious that these things have to be done. But what I'm trying to say is, I think we found the first necessary skill to finally solve the big problem we had. So peg and hold, so this insertion processes, have been proposed since the 80s, that this is, the problem of manipulation, but it was not solved, I would say, to an extent that we could, show it in a performance that was even close to humans. And finally, this was possible. And now we can really work on these questions. That's exactly what people are doing.
Just one more question, but it's more like industry, less technical. I mean, we've seen that with pre-training, it speeds up process vastly. So do you think maybe in the future, instead of being, because I think mostly robotic companies, as you said, like hardware, software is getting way more important, but maybe the hardware will be even provided for free or very low price, and we move to software solutions or like selling the pre-training cards.
Absolutely. I think the software has already increased tremendously in robotics. Otherwise, I mean, if you think, Google has also recently entered that race, right? So with Intrinsic, they built an alphabet company that basically tries to exactly do what you're saying. I'm not sure you can do for free, but I think the business model is very different. I'm actually quite convinced about that. Whether it's going to be a pay per X maybe case, right? So you pay per operation. Maybe that's going to be the case, or it's going to be such that you lease systems. I don't think that you will buy them anymore. I think it's more the shared idea. So you pay for a service, I guess, not for a software. Because in the end, the difference, I think, in anything that is supposed to do something productive, you care about the outcome, not so much about the way. Actually, no one cares about whether it's software or hardware, to be honest, right? It's not that it's important. It's important that the result is there. So if you want to produce something, if you want to deliver a coffee, if you want to get your parcel, I mean, the biggest robotics companies in the world are Tesla and Amazon, right? So what do you care about? You care that your parcel is tomorrow there. You care that your car doesn't crash, supposed to do the mobility service. So you don't really care whether it's software or not. It's more the service that matters, which I think is the question that has to be asked, because it's not just a mere software game, I guess, that has to be played. But I fully agree. I think they will change dramatically. Would be unwise not to. I believe this. And the second part, you had actually two questions, I guess. The learning of the models, and will they be pre-trained and delivered? Absolutely. There's also one reason why this has to be done. At the moment, at least the legal frameworks are not there that you can train in the field, because the certificates are gone. If you want to do autonomous driving and learn in the loop, you're in big trouble. It's actually not. So you need to be very well insured, I guess. So if you want to have a product that you need to solve the auto certification problem. I didn't talk about that, to be honest. This is a different story. Yeah, but it is important, because if we talk about real products like a car, it is a potential danger to your life, right? So it needs to be insured. It needs to be safe. It needs to be certified. It's like a drug. You cannot just invent a drug and then you can take it according to the Convention of Helsinki. So to do self-experiments as a researcher, sure, that's one thing. And then you might get a Nobel Prize for these kind of things, but you cannot produce and deliver it to people. So there needs to be the certification process, which typically is very costly. Audits are going to be more expensive than finance. So that's a bit of a hurdle we have at the moment for AI, I think, in general. That many things are, despite it's obvious they will be beneficial, it's very obvious, right? But then we run into many of these legal hurdles if you want to translate it into reality. So just to answer, that's why I think your comment is actually maybe right now even the only solution to deliver real AI systems for these kind of safety critical applications in reality.
Yeah, sure. For the talk was really inspiring. I have a question regarding your opinion about deep learning models. I know that you have probably, or you can prove the advantages of, for example, your algorithm with the very high demand resources aspect of deep learning models. But I want also to understand what your point of view in general, like besides the robotics field. What do you think about it? Because this is a problem that they will always require a lot of resources. So what do you think in general?
Okay, that's a very, I think, important question, because ask the question, is a deep learning network an AI system or not? In the sense of, I think one limitation we have to a large extent of deep learning is incremental learning is possible only if you're very lucky, and it's more anecdotic, I would argue, right? It's not really there's no real theory that we understand how to set up a network. I'm sure pretty many people will disagree, but I mean, I'm a theorist myself, so I mean theory, not gut feeling. So I think there's more to it, obviously. There has to be some. I think what I'm trying to show here is if you bring together, models, which is theory at the end, and these learning processes, which are the same, right? It's not that it's different. Something happens, something very interesting happens. And it's orders of magnitude that happens here. It's not incremental. It's a game changer. And I would probably argue that one of the goals we should probably have in mind is incrementality has to be part of what we consider learning. Because if we cannot show that something gets better or worse, is this really learning, or is it just a mathematical function approximator? And I'm happy to also, I mean, it's fine to have a function approximator. Not that I have anything against it, but we talk about AI, right? I think it should have interpretation. AI cannot just be emergence if it's not truly emerging, right? If it's just anecdotic, I think there's a limitation. So my point is, if you look at the big success of deep learning, that is unquestionably there. It's amazing what people have done. But it's also clear why it has been there in computer vision, right? I mean, ConvNet is basically it's learning filters, right? Classical filters, which are just, many of them. So basically, you could argue, well, that's a model, right? That's kind of a model of edges, and these convolutional kernels are, at least they have the notion of what, they're connected to the visual problem very, very intensely, and that's why they work quite well there. And I think I gave the same argument for physics, which unfortunately the equations are so much more complex. I cannot. I'm sorry, it is like that, right? But I mean, the 2D image with edges it's a line problem, and if you look at physical systems, it's unfortunately it goes into manifold. It's a mess, right? It's much more complex theory. But I would say that maybe the same argument why the original work, also when Trustworthiness published his work, was so successful, is because there was a notion of the domain, right? So and then we call this domain knowledge. Call it whatever you like, but I think it basically is the key to transferability, to solving these data intense problems. I mean, prior knowledge basically means we need less data. So, and I think needing less data is a good thing. It's not a bad thing. It's a very good thing because it means less time, less resources. It's, let's say, for a scientist, it's more beautiful, it's more elegant, right? Which is not an objective argument, but it's at least a kind of artistic argument, at least. So yeah, I think that's my stake on it, and I think it's actually great that we have this advance because it also shows how much we can do. That's why I said the word GPU so often, because I really think it shows so well how much you can do if you don't forget, the co-design problem, because this is what enables the scaling. And I think if you listen to the grandmasters of deep learning, they start to say very similar things in their own words, which I think is great, because we're running into many limits at the moment. And I think it's rather clear in many dimensions why we have that. One thing I think is really important about deep learning is also this explainability aspect. If you use it in systems where you need to explain the decisions that are being made, and not only due to technical reasons, but maybe there's legal reasons, right? Many of them are there. Then I think it's important to understand why decisions were taken. So also explainability is a very strong argument. Then there comes this word of trustworthiness, which is many aspects. And another thing why I think deep learning has progress also in these directions is safety. If you want to have an AI system in the field, like really in the field, you need to be able to show safety, which means guarantees of boundedness, for example, convergence, all these kind of things, which are well established in aerospace, for example. I think that's very important to mature, in the field. Welcome.
Yes, sure. I have a question. It's it's related to this first question. So a lot of progress these days in computational linguistics, computer vision, is made those huge training models. So to what extent this is the way that you think speaking of robotics? Is it even something that is potentially applicable there? Because I can imagine there are different kinds of problems. Yeah. And then you have like also talking about motion, about sensing and about interactions. And it can be that this is applicable to something. And again, also my view is that the complexity goes in that direction. You didn't really touch any of my second questions. Started with, okay, who is this human there? And then the question is, are we related? We still need the human. And well, yeah, the work by itself. And on the other hand, the thing is, maybe what can we learn from the interaction?
Yeah. Okay, that's three questions actually, three very big ones. So let me try with, I go back in time, that's fine. So what can we learn from humans? A lot. So the last slide I gave, I think, was, let's try to put humans in the loop. You see the lower one? I think it's everything. Everything we can learn, not only in the design, in the algorithms, everything is basically human inspired to some extent, I would argue. And even if it's just, what do we want to achieve in terms of performance? And if we go to interaction, on purpose, I didn't talk about physical interaction, cognitive interaction, all these levels that I think the first question was really pointing down to. I think this is really where the human is key, obviously. So especially if you want to work in a human environment, it's the human that you draw inspiration from and understanding to interact in the human environment. So the human is the source of understanding and of learning, I would argue, right? But we're still a little bit far from that because we're not yet there that we can fully deploy these kind of systems in human environment. So the data problem is still there. So I think this is about to come. Now with these breakthroughs, I think the door is open now to allow that. Right now, the human is more the teacher of the robot to get skills, and more the robot will learn from human observation and interaction more than in its natural habitat, I would argue. Right? I think this is something that's more and more happening. Which, for example, in a very low-level example, I didn't show it, is in rehabilitation, we do this already now. So a robot learns from the interaction with the patient what's the right assist is needed strategy. So we actually had a collaboration with a small company in Germany that had the first FDA-approved AI in rehab. So it was an AI algorithm that basically tries to optimize the physical assistance to a post-COVID patient or someone with a stroke, surgery in the hip, and so on and so forth. But basically, the interaction with the human in that in physical terms is improving the control and the assist of the robot itself. And the same thing we did also for basically pain detection from human patient recognition. With colleagues who are really known in that field, we close the loop on that level, for example. So I think this is more and more going in that direction. But you need humans and robots in one space. That's why this getting the safety gears away, and that we can actually really integrate them, not only in the lab but in bigger, large-scale experiments and field studies. That's, I think, crucial to truly tackle that problem. Then I think maybe to the first question, because I'm not sure I got the second one. The first one was basically on this. It's kind of related to that one, obviously. So speech and I think even cognition in general, or cognitive interaction, is very important in robotics. But due to the same argument I gave in the last one, I think is in order to truly train these systems and leverage from the great advancements in deep learning, on a full scale, we need to create environments in which we can get that amount of data to train the models to be suitable and to be useful. I think that's an exercise we have to do. So I think we can always show this anecdotally, interactions between humans and robots, and they typically are not an Alexa type of interaction, right? Humans have all these weird ways of interaction, which you know much better than I do. But I think, repairing the interaction, doing all kinds of, in the middle they break and then change the path of the course of interaction itself. It's it's highly dynamic, right? It's not just a plan and then follow, but it's an interaction process. And in order to fully understand that, I think it's important to see how humans also respond to robots, because it will also be a learning process, because the interaction itself, I think, will evolve over time, because humans in the beginning, they will interact differently with the robot than they will do 1 year later, for example. So I think that's a process that also has to be understood. So it's not a single shot problem, I guess. Yeah, does this roughly touch the first one? And the second one was, I'm sorry.
Yeah. Well, the first one, right? So what we have been doing, for example, in computational physics, natural processing, we have been inventing some artificial problem that allows a system to work from a lot of data to understand human language in general. And then you can take this and like fine-tune it to a whole bunch of problems. The question is, do you see anything like that theoretically possible? Maybe for certain kinds of aspects, is there maybe some fundamental task that you can actually solve in this way, and then kind of in this knowledge gives you a very good start. You actually need to learn something a little bit different, maybe in a little bit more specific environment, maybe with a little bit different kind of hardware.
Yeah, it sounds like, yeah, absolutely. I think if this is possible, which I would assume, I think this would be fantastic, especially maybe not so much, and this has different reasons why it's not yet, I think, maybe so important for industry. But if you think about all the healthcare applications, I see so many real cases there that would need that kind of interaction. So they need robots that are not only assistants, but they are interaction partners, so that they can really communicate with the person. I mean, if you could deploy these kind of systems, for example, in spaces for the elderly, or even if you have logistics, could also be an example, right? One person is interacting with many robots, and he's for the error recoveries and do a natural interface. Humans like to interact also with machines naturally, so they don't want to learn a new device necessarily. I mean, they can appreciate it if it works, but I think ideally, I would say that the natural communication via speech is one of the most preferred ones. And I think one aspect that has to be dealt with there is, at least so far what I have seen a lot, is the perception problem on the robot side. So often, I think the language part, the theory, the methods are there a lot, but then there are these problems. I'm not an expert, obviously, but who's talking to me? There's many people. How do I concentrate? How do I? There's all these aspects that if you bring a robot in the real environment, they become then very challenging. So I think if you can nail them down to some extent, there's many cases that would be very, very important. Also, another one, that's maybe maybe I actually see one case where it would be really wonderful to have it already today: surgical robotics. So if you have now that surgical robots have been this tool for many years now, so minimally invasive surgery. So you're sitting at this console as a surgeon, and you interact minimally invasive, through these choker points with robots who have the body, and they are mostly direct tools. They are not yet autonomous or semi-autonomous. So, but if you now want to basically interact with the robot and tell them, go there, do the surgery, go close to the red dot, and I don't know, do a cut of 1 centimeter, right? And then one of the robots goes there, does it in order to support you. So it's like this very intuitive system that you don't have to program or learn a new interface. I think that's something I've been interacting with many of the surgeons over the last years. They would be very happy to have this kind of natural interface. And I think you wouldn't deal with the same problems I was just talking about before with many humans, because one surgeon talking to this robot. And I think this could be a very good case. That is, I think, very relevant. So it's a huge environment, huge industry. Surgical robots is, I think, at the moment, next to logistics and autonomous cars, I would say the third biggest one nowadays. Okay.
That was recent experiment. I saw national interest in Korea about this, about this thoughts interacting with robots and all the microsurgery. There's a paper on that.
Yeah, that's actually true. And there was also, it's a good point. There was also just recently from, I think it was the Johns Hopkins group as well, They did a similar, I think it was a Nature paper just recently, and they tried to bring it to this, let's say, more cognitive level. So not anymore only on motoric level. So, but this also works because now you have robots that they can take away this motoric burden from you. Because if they are pure position control, then there's always this limitation they have. So in order to free yourself from this, I have to control everything, then it becomes actually possible. But I think this is still in study progress. It's not yet in reality, but in first experiments they did. Yeah, absolutely. Great. Right. Thank you very much.